This is the first lecture from Chapter 16 about acids and bases, and this first lecture will focus on an introduction, which is some definitions as well as how to calculate pH and pOH. Well, first for a definition, acids are recognized because they have a hydrogen attached to an electronegative atom. So, for example, it's not just any old hydrogen. See how this hydrogen is directly attached to an oxygen? In this case, the hydrogen is attached directly to chlorine. And so it can't be any old hydrogen. For example, if you're looking at methane, CH4, these hydrogens are not considered acidic because carbon is not an electronegative atom. You'll see that there tends to be a main division of acids from binary acids and ternary acids. So binary acids contain only two different types of atoms in them. Notice that I didn't say two atoms, I said two different types of atoms. So for example, this would still be a binary acid because there are two different types of atoms, even though there are 3 atoms total. Then there are ternary acids, which are most typically oxyacids, acids that contain oxygen. So if you count the types of atoms, you will find there are 3. There's sulfur, there's oxygen, and there's hydrogen. All right, so general properties of acids include sour taste, and so Sour Patch Kids and all the different types of sour candy are sour because they have acids in them, typically citric acid, so harmless ones, but they do have acids. That's how they get the sour taste. Acids will react with many metals. You may have heard a suggestion, kind of a online suggestion to clean off battery terminals that have corroded with something like Coca-Cola. And that's because of the acid in Coca-Cola. And again, most acids will actually react with metals, which will dissolve them away. And of course, I think you realize they react with bases. And when you combine an acid and a base, you end up with a neutral solution. And they turn blue litmus paper red. And just, it's kind of fun to look at some of the very, very common uses of acids in our household. There are a lot of acids in food items, and actually that's how your stomach dissolves food. Stomach acid is hydrochloric acid. There are acids that make batteries operate, particularly automobile batteries. That's why they can be so dangerous, actually. You never really want to stand over one if they're at risk of leaking or exploding. Acetic acid is what is used in vinegar. And so I don't need to go one by one. Well, one more. Carbonic acid, carbonated beverages. That's how we get CO2 into our carbonated beverages, is by adding carbonic acid. All right, bases, on the other hand, taste bitter. Mustard is quite basic, so that kind of bitter, pungent taste is typical of a basic solution. You may often hear the word alkaline, like alkaline batteries. That's kind of an old-fashioned term that means the same as basic. Bases feel slippery. Okay, so that's why there's often a base in a soap. Cleansing materials are often basic, and so that's why they often feel slippery. And they turn red litmus paper blue, kind of the opposite of what acids do. And of course, they react with acids. Again, when you combine an acid or a base, you can end up with a neutral solution. And some common bases, as I said, soap. In the olden days, or if you read old books, they'll mention lye, which is kind of the old layman's term for base to clean your, actually people used to clean their bodies with it. So If you read these old books, it'll say something, oh yeah, Mama scrubbed my skin with the soap until it was raw. Well, that's because the soap had such high level of base back then. Okay, baking soda is basic, sodium bicarbonate. That's quite often used to neutralize acids spills. Antacids that you take for heartburn neutralize your stomach acid. And cleaning agents. Ammonia is often put in cleaning agents, and that is basic. Alrighty, so let's talk about the chemistry of acids and bases. And again, you can recognize an acid because it has a hydrogen ion that is donated. And bases, the original definition, which was by somebody named Arrhenius, define bases as producing hydroxide ions in aqueous solution. There is a more recent definition that's a little bit broader than that. But I want you to realize that anytime you're talking about aqueous solutions and you have hydrogen ions or hydroxide ions, that solution likely has a pH that is not neutral. All right, so, and again, this is just kind of so you don't get tripped up later. You will often see the hydrogen ions produced by an acid just on their own like this. However, in reality, in aqueous solution, this guy, the hydrogen ion, is very reactive and not quite very stable on its own like that. So typically, a hydrogen ion will hop onto the back of a water molecule and produce what we call a hydronium ion, and that is really how hydrogen ions exist in aqueous solution. But I want you to be aware that for our purposes, the hydrogen ion is equivalent to the hydronium ion. So either one of them indicate an acidic solution. The more current definition of acids and bases, the acid definition is the same. Acids are a proton donor. At this point, you may not have thought or realized that a hydrogen ion is actually all it is a proton. How is that possible, you may say? Think about a neutral hydrogen atom. So a neutral hydrogen atom has one proton in the nucleus. There's no neutron in the most common isotope of hydrogen. And then it has one electron outside of the nucleus. So if you have the hydrogen ion, that is with a plus sign, it means what? It means you have removed an electron. And so all you're left with is a proton. So hydrogen ion is in fact a proton. What's different in the more current Bronsted-Lowry definition of acids and bases are the definition of a base. A base from the Bronsted-Lowry definition is a proton acceptor. Remember what Arrhenius said. Arrhenius said that a base produced hydroxide ions. So a Bronsted-Lowry base is anything that accepts a proton. So the Bronsted-Lowry definition is more broad. So let's look, for example, if you look at something like ammonia, which is a base, very, very common base. If you didn't already know that, you should. And it alone doesn't contain any hydroxide ions. However, if you add it to water, it will act as a base and it will accept a proton from water, okay, to make ammonium hydroxide. So it does function as a base, and it's included in the Bronsted-Lowry definition. So if you're looking at chemical equations of an acid, you can see them commonly shown two different ways. Even though we really should always show water if it's an aqueous solution, quite often chemists will do something like that. Okay, they'll say, okay, HCl, when you put it in water, it's an acid, and acid dissociates into hydrogen ion and the accompanied anion. And so I just want you to realize that whether you see an acidic substance represented like I just wrote or represented as forming a hydronium ion, they're considered equivalent. So get very familiar with writing equations, chemical equations showing how an acid or a base behave in water. So remember that bases are proton acceptors, and so these reactions are very, very easy to write because all you're doing is transferring a hydrogen from one substance to another. So if you know what the base is, and ammonia you just have to memorize, it's going to accept a hydrogen from whatever other substance is around. In this case, water. Okay? So water is going to donate one of its hydrogens, and you're going to end up with then NH4, that's just NH3 plus an H, and OH minus. Now keep in mind what you're transferring is an H plus ion, not a neutral hydrogen ion. And so the charges are going to change, and that's an important realization. Whatever you add the H plus to will gain a positive charge, and whatever you've taken it away from will be left behind with a minus charge. All right, just simple vocabulary. There's something called amphoteric substances, and those are substances that can either act as an acid or a base depending on what they're around. So water is probably the most common amphoteric substance. In the presence of an acid or a proton donor, water will act as a base and accept a proton and become a hydronium. However, water in the presence of a base will act as an acid. In other words, it will donate a proton. All right, so here's the first important concept with acids and bases, and it can get a little tricky. And that's understanding what conjugate acids and bases are. I'm going to give you the definition, and it probably won't make a lot of sense until you see examples. So a conjugate acid is the product that's formed after a base accepts a proton. So let's look at that for a minute. Here's, in this case, water's acting as a base. It's going to accept a proton from hydrofluoric acid. So water, once it accepts a proton, becomes H3O, okay? And so H3O is now the conjugate acid of water. Well, you'll probably have to go through this several times before it makes a lot of sense, so don't worry. A conjugate base is what's left over after an acid has given away a proton. So let me just stop for a minute. A conjugate acid comes from a base. Okay? A conjugate base comes from an acid. Okay? So a base makes a conjugate acid. An acid makes a conjugate base. And we call those conjugate acid-base pairs. So back to a conjugate base. You start with an acid, so identify your acid. That's what the A stands for, hydrofluoric acid. After it's done its thing, acids donate protons. So after it's done its thing, what are you left with? You're left with the conjugate base. Okay? So now you might be asked, what are the conjugate acid-base pairs in this reaction? So you want to connect the things that came from each other. So here's the acid goes with the conjugate base. Okay, they obviously come from each other. They both have the fluorine. And the base forms the conjugate acid. They're obviously associated with each other. There are two conjugate acid-base pairs in any acid-base reaction. So there's a worksheet on identifying conjugate acid-base pairs, and that's an important one to begin to work to get this concept down because it can get confusing. So if you're given a chemical reaction equation, such as shown here, and asked to label each substance, You're going to identify the acid as the substance, typically the one that starts with an H. Now, of course, water also starts with an H, but look for another one, okay? So that's your acid. The other substance, in this case water, will be your base. Now, look for what, once the acid does its thing, which is donating a hydrogen ion, what is it going to form, or what's going to be left over? It's going to be left with NO2 minus. So here's the conjugate base that comes from this acid. In this reaction, water is serving as the base. In other words, it is accepting a proton. The product that's formed when that happens is the hydronium ion. So here's your other conjugate acid base. And here's basically what I just talked through on the last slide, but in case you prefer to have it in the written word instead of my verbiage. All right, so now after you practice with a couple of chemical reactions, you need to be able to also write conjugate acids and bases simply by being given the chemical formula of one. So if I tell you, let's ignore these bottom one labels right now. If I tell you these are the acids, would you be able to draw the conjugate base? Well, the main thing is to remember what an acid does. An acid donates a hydrogen atom. That's how you make the conjugate base. So if you have HCl and you give away a hydrogen ion, what are you left with? Okay, and so chloride is your conjugate base. Same thing here, sulfuric acid. If you give away a hydrogen ion, what are you left with? Watch your charges. If you're giving away an H+, what's left behind takes on a minus charge. Okay, let's do one more. If your acid is HSO4 already with a minus charge and you give away another hydrogen ion, you're left with SO4. Now your charge is -2 because you had -1 to start with. So go through the rest of these. Make sure that you're comfortable doing this. Here is some practice for you. So I want you to label each substance, each of the two reactants, each of the two products. So I would put the video on pause and then I will discuss the answer with you. Here's how I would start the problem. I start out by identifying what the acid and base are. I see, since HNO2, which happens to be nitrous acid, it's the acid because it begins with a hydrogen, which means water in this case is functioning as a base. Now I want to look at what is HNO2 form what's left over once it gives away the hydrogen atom. And that is NO2. So that is your conjugate base. And here's your first acid, conjugate acid-base pair. Now, since we know water's functioning as a base, what do bases do? They accept a hydrogen ion. So once water accepts a hydrogen ion, it becomes hydronium ion, and so that is the conjugate acid of water. I don't know if you have thought to wonder why a base makes a conjugate acid and an acid makes a conjugate base. How does an acid become a base? Well, that is because if you think about this reaction in reverse, so if you were starting with the products as reactants, okay, so if you're starting with NO2 minus and H3O plus and going to the left, the H3O plus would be acting as the acid. It would donate a hydrogen ion to the NO2 minus. So in the reverse direction, the conjugate acid is what does in fact act like an acid, and the conjugate base does in fact act like a base. So if you have an acid on one side of an equation, it's going to be a base on the other side of the equation. All right, so let's look at the second reaction. Now, one of the things you simply need to memorize is when you see a nitrogen with a neutral nitrogen containing compound, you need to think of base, okay? Those are very common hydrogen ion acceptors. and this isn't really something we get into, but you certainly will in organic. Nitrogens, if they're neutral, have a lone pair of electrons on them, and that lone pair of electrons is a very good snatcher of hydrogen ions. So that's going to be your base, which means in this case water is functioning as the acid. Let's look at the base, and we know they accept hydrogen ions. What is it going to form once it does that? Right here. So that is going to be your conjugate acid. Remember, bases make acids. And your acid, water, which is going to be the proton donor, once it donates, is going to make hydroxide. So that will be your conjugate base. Let's look at a minute at acid-base reactions, and this is if you put an acid into water, it's in effect an acid-base reaction because water can act as an acid or base. But now I'm talking about strong acids and strong bases where water is not the preferred reactant. So if you have a strong acid and a strong base in water, what you are going to make is water and a salt. Okay? So overall, what you have done is you've gone a solution with an acidic and basic substance and made an entirely neutral solution. They essentially annihilate each other. And so it's just kind of important to remember that combination of a strong acid and base make water and salt. Remember, salt is the nickname for ionic compounds. Now that leads us into the last part of this lecture, which is teaching you how to calculate pH and pOH. So it's important to understand actually where the concept of pH comes from. It turns out that pure water does something we call auto-ionize. So in any neutral water solution, there is a very small amount of ions present, hydronium ions and hydroxide ions. That's just normal, not very much, but a bit of it. But in neutral water, there are equal amounts of each of these ions, okay? And so that's why it's neutral, okay? They're equal amounts. Now, in aqueous solution, if you add additional ingredients, you can disrupt the ratio of hydronium and hydroxide ion, and that is where the concept of pH comes from. In our calculations of pH, we will use something called kW. I told you there were a zillion different equilibrium constants. Well, this W stands for water. So if you were to write the equilibrium constant expression for the auto-ionization of water, you would get products over reactants, right? So we have hydronium ion concentration times hydroxide concentration. The reactants are liquid water. Remember, you leave pure liquids and solids out of the expression for kW. So the kW expression for auto-ionization water is simply concentration of hydronium ion times concentration of hydroxide. In a neutral solution, both of these are equal to one another. And at room temperature, each of these concentrations is 1 times 10 to the minus 7 molarity. So that's very small, that many moles per liter of ions in aqueous solution. And so the kW at room temperature at 25 degrees is 1 times 10 to the minus 14. That's an important tidbit to know because you're going to use it quite a bit in your calculations when you're trying to convert from hydronium to hydroxide. Now, obviously, if you add an acid or a base to neutral water, you're disrupting the ratio of hydronium and hydroxide ions. And so let's look at this would be an easy calculation. For example, what if I asked you to calculate the hydroxide ion concentration when the hydrogen ion concentration is 3.6 times 10 to the minus 3 molar? Well, as long as it's at room temperature, which you assume unless you're told otherwise, the product of these two ions will always be 1 times 10 to the minus 14. So if you are given the concentration of hydronium ion, all you have to do is solve for the concentration of hydroxide because we know Kw. It's 1 times 10 to the minus 14. So take a look at how we would do that. Here's our equilibrium expression. Again, as long as you're at room temperature, Kw is 1 times 10 to the minus 14. They just gave us the concentration of hydronium ion. So now we're going to solve for the concentration of hydroxide. And it turns out 2.8 times 10 to the minus 12. So again, even though I said this, I'm going to say it again. All aqueous solutions, no matter what the pH may be, contain both hydronium and hydroxide ions. Even if it's a very acidic solution, you're going to have some level of hydroxide. It's the balance of those two that determines pH. So if you have an acidic solution, that means the concentration of hydronium ion will be larger than that of hydroxide. Okay, in other words, greater than 1 times 10 to the minus 7. Basic solutions will have a higher concentration of OH than hydronium. The formula we use, and I would jot this down someplace where you can refer to it regularly until you have it committed to memory. pH, which is the value that we use to measure acidity in solution, is defined as minus base 10 log of the concentration of hydronium ion. So pH depends totally on the concentration of this hydronium ion. And many acids will not even function as an acid unless they're an aqueous solution. So, all right, so in general, of course, if you put an acid in water, that raises the concentration of hydronium ion, which means the pH will be less than 7. So you'll probably want to look at the math and prove that to yourself. But because we're dealing with log, minus log, if you have a very high value for hydronium, you're going to have a very low value for pH, kind of an inverse relationship, a little more complex than that. But bases will have pH greater than 7. Okay, so just another way of putting it, the lower the pH, the more acidic the solution. The higher the pH, the more basic. So anything with a pH greater than 7 is basic, and anything with a pH less than 7 is acidic. Because it is a log scale, one step difference in pH represents a factor of 10 times higher in hydroxide concentration. So the most common range of pH that we deal with is from 0 to 14. However, it's important to realize that you can have pH values that are negative. You can have -1, -2. That just means it's an extremely acidic solution with a very high molarity. We will also be working with what we call pOHs. So if you're dealing with a reaction where it's more important for you to keep up with a concentration of hydroxide than hydronium, pOH might be what you work with. So at this point, it's important to emphasize anytime you see this lowercase p in front of something, that means minus log. Okay? So little p means minus log of whatever comes after it. And it's also important, do you remember how to get rid of a log base 10? It is, you take 10 and raise it to the exponent of whatever. So we'll do a bunch of examples of these on the next few pages. It might be helpful to remind you what log means. When you take the log of something, you're basically looking at the exponent. What you're doing is you're taking whatever the exponent is and bringing it down as your main number. So, and the fact that you have a minus here, so you bring down a negative exponent, and this minus is going to make it overall become positive. So why do we deal with logs? We deal with logs in calculations where we have very small or very large numbers. Numbers with exponents, large exponents or small exponents. It's just easier for people to deal with a value of 7 than a value, for example, of 1 times 10 to the minus 7. That's the whole purpose of log scales. Now, because the concentration of hydronium ion times the concentration of hydroxide ion in solution at 25 degrees is always 1 times 10 to the minus 14. That's always the case. Remember, that's kW. Because that's the case, if you do a derivation, what that means is that pH plus pOH is always equal to 14. So that's a handy little equality to know also. Let's do some simple examples. Calculate the pH of an acidic solution at 0.0034 molar. So pH equals minus log of whatever the concentration is. And the problem told us 0.0034 molar. So find the log button on your calculator, and remember, when you get the log value, take the negative of it, and that is your pH. You should have gotten 2.47 as your pH. Now remember, any pH less than 7 is acidic. This is going to be very weird what I'm telling you. I'm probably going to have to tell you a few more times, and that is about sig figs. Sig figs of logarithmic numbers are very odd. Any digit to the left of the decimal place on a logarithmic number simply represents the exponent. Remember, logs just take the exponent and bring them down. So this 2 represents the exponent, which really tells us nothing about the precision of a measurement. So in a logarithmic value, the only digits that are considered significant, in other words, have something to do with the precision of a measurement, are to the right of the decimal. Okay. So again, the only digits in a logarithmic value that are considered significant are those to the right of a decimal. So 2.47, pH at 2.47, since it's a logarithmic value, only has 2 sig figs. Here is just a summary of everything. Okay, so remember, if you are dealing with an acidic solution, you have a higher concentration of hydronium ion. Remember that for our purposes, H plus is equivalent to H3O plus. You're going to see them both ways. In a neutral solution, hydronium and hydroxide are equal to each other, and in a basic solution, hydroxide ion is larger. What if we have to go in the other direction? What if we're given pH and we're asked to find the concentration of hydronium ion? Okay, so how do you get rid of log values? You remember how to do this? Log base 10. Okay, so what you do is you have to take 10 and raise that up as an exponent. So if we have the reaction or the equation pH equals minus log concentration of hydronium, and we want to isolate, we want to be able to solve something for the concentration of hydronium, what do? We take 10 and raise both, raise it to the exponent of pH, and we do that to both sides, and so we have 10 with this log whole term becoming our exponent. Now, a 10 and the exponent log cancel each other out, and so what you end up with then is 10 to the minus pH equals concentration of hydronium ion. All right, so for this problem, you simply would say 10 and take the minus pH, so it was raised to minus 3.52, and that will equal your hydronium concentration. Make sure that you have the right key in your calculator, especially using the calculator that you will take your exam with. And make sure that you get this value, 3 times 10 to the minus 4 molar. Sides of the equation. So as I said earlier, anytime you see a lowercase p, that means take the minus log. Okay? In this case, the minus log of concentration hydronium ion. So we have pH, we have pOH, we have something called pKw. So P means minus log of, right? And KW. KW, unless we assume that it's at room temperature, is 1 times 10 to the minus 14. So pKw at room temperature is 14. And as a reminder of the relationships, you'll be using them as conversion factors. The concentration of hydronium times the concentration of hydroxide always will equal 1 times 10 to the minus 14 at room temperature, which is where we're working. And pH, okay, plus pOH will always equal log of Kw, which is 14. So these two equivalencies are important to know. Because of the equivalency of hydroxide and hydronium in a neutral solution, so I'm going to rewrite what we know Kw to be. So the product of hydronium times hydroxide will always be a constant, Kw. And so as one goes up, the other must go down, right? If Kw is going to stay constant, they're inversely related. And that is, of course, the case. If you have a pH of 14, you will find that your pOH is 0. If you have a pH of 8, your pOH is 6. So remember the equivalency, pH plus pOH equals 14, that's at room temperature. So you can solve for one of them from the other. pOH would be then 14 minus pH. I show this table just for you to see the really cool relationship. So notice that all the pOHs and pHs add up to be 14. Okay, all in aqueous solution, they all have to add up to be 14. And also notice that hydrogen ion concentration times hydronium must multiply together to give you 1 times 10 to the minus 14. So just as a quick look, the exponents will generally add up to 14 for hydrogen ion concentration and hydroxide concentration. In case your mind is hurting a little bit, we'll do something easy, and that's a definition for strong acids and strong bases. The definition for both is that they ionize completely in solution. So if you have a strong acid, which just will give the generic formulation of HA, and you put it in water, it will 100% dissociate into the hydrogen ion and the conjugate base. Okay, that's 100% if it's a strong acid or base. So obviously, if you're going to show that as a hydronium ion, it's going to be, instead of a naked hydrogen ion, it's going to be a hydronium ion in the conjugate base. That's a strong acid. There aren't very many. There are only 6 strong acids. You do need to commit them to memory, so write them down someplace. Every other acid that anybody will mention anyplace else is a weak acid. If you have a weak acid, okay, so I'm just going to write weak down here. If it's not one of these 6 and you put it in water, it's still going to donate hydrogen ion as all acids do. However, whereas we had 100% ionization in a strong acid, we might have something like 1% ionization in a weak acid. and the bulk of it will still be in the intact acid form. So that's the difference between strong and weak acids and bases. So here's a typical problem for you. Calculate the pH of a 0.050 molar HCl solution. Now, HCl is one of the 6 strong acids. Why do we care? Because since it's a strong acid, whatever concentration we started with before we added it to water is going to be the concentration of the hydronium ion in the water. So we start with 0.050 molar. We're going to end up with 0.050 molar of hydronium ion. This original intact HCl is going to be gone. Now, once we get into weak acids that do not dissociate completely, whatever concentration you start with or a weak acid is not going to be the concentration you end up with of hydronium ion. And remember, it's the hydronium ion concentration that determines the pH, nothing else. So now that we know the hydronium ion concentration to be 0.050, we can calculate pH simply by taking the negative log of it, and this solution would give us a pH of 1.3. There are a handful of strong bases also with the same definition. If it's a strong base in water, they will dissociate or ionize 100%, and none of the original intact base will be left. So what are the strong bases? All of the hydroxides that are made with group 1 metals, so that's sodium, potassium, cesium, lithium, etc., those all make strong bases. So any of these bases, let's just take sodium hydroxide, when you add them in water, they will dissociate into the hydroxide and the metal cation, and they will do so 100%, so that you have 0% of the original intact hydroxide. And again, calculations with strong acids and strong bases are very easy to do because whatever the original concentration of the strong acid or base is will end up being the concentration of the ion. Now, it can get just slightly tricky. There are more strong bases. So I said all the group 1 metals, lithium, sodium, potassium, make strong hydroxide bases. But also the heavy group 2 metals make strong bases. So what do I mean by heavy? Barium and strontium are at the bottom of group 2A on the periodic table. Those are the heavy group 2 metals, and they make strong bases. So what is the pH of a 0.035 molar solution of barium hydroxide? Now, barium hydroxide, since it's a heavy group 2 metal, is in fact a strong base, and so 100% of it will dissociate into, or will ionize. You have none of this original left. What you have to look at, though, is stoichiometry. Barium hydroxide has 2 hydroxide groups for every 1 molecule of barium hydroxide. So the concentration of hydroxide, once you dissolve barium hydroxide in water, is 2 times the concentration of the barium hydroxide, okay, or 0.070 molar. Therefore, now also if you're dealing with a base, you're going to have to find pOH first, okay? That's the minus log of the concentration of OH, minus log of 0.070. So pOH is 1.16, but the problem asks for pH, not pOH. So now you have to remember that pH plus pOH have to equal 14. Okay, so if pOH is 1.16, pH is 14 minus 1.16, or 12.84. And so here are a couple going in the other direction. These are asking for the concentration of HCl that was added if the pH of the solution is 3.75. So remember, concentration is 10 to the minus pH. Now, it isn't really concentration of the intact acid, it's concentration of hydronium ion. But for strong acids and bases, because they 100% dissociate, these are equivalent. Okay? Concentration of the original acid will equal the concentration of hydronium ion because it all gets converted. And we find that by 10 to the minus pH. So for this problem, it'd be 10 raised to minus 3.75. So go ahead and punch that in your calculator, see what you get for pH, and then we will work the next one. Well, I'm hoping when you raise 10 to the minus 3.75 in your calculator, you got an answer 1.8 times 10 to the minus 4 molar as the original concentration of HCl. Looking at the second question, if you have a pH of 11.60 and you're looking for the concentration of KOH, I'm hoping that you notice there's a little bit of, ooh, I didn't mean to do that. There we go. A little bit of discontinuity here because the problem is giving you a pH value, but the substance is KOH. So since you're trying to get to KOH, I would rather be working with pOH. So let's get this pH in terms of pOH first. So remember, pH plus pOH equals 14. So pOH will be 14 minus 11.60, which is 2.40. Now that we have pOH of 2.40, we can find the concentration of hydroxide, which equals the concentration of KOH since it's a strong base, and those equal 10 raised to the minus 2.40. And again, try putting this in your calculator to make sure you're doing it right. If you have 10 raised to the minus 2.40, you should get that the concentration of hydroxide, or concentration of KOH, they equal, since it's a strong base, equals 4 times 10 to the minus 3 molar. Try the last couple problems on your own, and then I would recommend going to the worksheets for calculating pH, pOH, and concentrations, and doing a whole bunch of them, because the rest of this chapter and the next one is all about equilibrium of acids and bases and ice tables, weak acids and bases, and it gets quite complex. So it'll be very helpful if you have these simple calculations down pat. So I would turn off the video. So if I were solving this, I would again notice that I'm talking about hydronium ion concentration, right? Remember I said think of those as equivalent. Okay. And yet, now I'm talking about pOH. So I have a mismatch here. So they're asking for pH, so I'm going to try to convert this to OH or pOH. So there are two ways to do it. I can either convert the hydronium ion concentration to pH and then convert pH to pOH, right? Or I can convert the concentration of hydronium ion first to the concentration of hydroxide and then get pOH directly. So you can do it both ways. So let me try this route just because we haven't really done that yet. You have to remember that the concentration of hydroxide times the concentration of hydronium equals Kw, which is 1 times 10 to the minus 14. All right, so if we plug in the value we have for hydronium ion, we can solve for the concentration of hydroxide. So the concentration of hydroxide in this case would be 1 times 10 to the minus 14 divided by 0.00001, which is 1 times 1, 2, 3, 4, 5. 1 times 10 to the minus 5. Let's see, 14 minus 5, so that's 1 times 10 to the minus 9 molar should be the concentration of hydroxide. And once you have the concentration of hydroxide, it's easy to find pOH. pOH is simply minus log of that concentration value, which is 1 times 10 to the minus 9. And remember, log simply takes the exponent. So pOH equals 9. Alrighty, so the work that I've shown here is using the other pathway. And as you work more and more of these, you realize there are typically 2 pathways to do these conversions. So just get familiar with both of them. One more, and then we're done. If I give you a pH, if it's 10.6, which is basic, what is the concentration of hydroxide ion? So I recommend turning the video off and working it out yourself. You might even ask yourself, what are the 2 different ways I can work this out? Well, if you're starting with a pH of 10.6 and you're trying to get to the concentration of hydroxide ion, the 2 paths you can take would be first convert to pOH, right? And then convert to hydroxide. Or another approach that you might take, let me get rid of this. Another approach that you might take would be to convert the pH to hydronium ion concentration, and then convert hydronium ion concentration to hydroxide. I prefer the bottom route. It's just easier for me, but they will both give you the right answer. Alrighty, so we know the pH is 10.6, so the pOH is going to be 14 minus 10.6, or 3.40. Once you have the pOH, you can find concentration from 10 raised to the minus pOH. When you plug that into your calculator, you get hydroxide concentration of 4 times 10 to the minus 4. That is it for this very lengthy lecture. It was hard for me to make it so long, so I apologize for how long you had to listen.